Let's try these limits and see how they go. We'll start with the limit as x approaches negative infinity of x squared over e to the negative x. So the first question we have to ask is, what is the limit as x approaches negative infinity of the numerator? Well, that's the same thing as negative infinity squared. Well, negative times negative is positive, and if you take something extremely large and square it, it gets extremely large, so that's going to be infinity, which looks like it might be a L'Hopital situation. So let's take a look at the limit of the denominator. This one, we're going to take e raised to the negative infinity. And sure enough, e raised to the positive infinity is very, very large. In fact, you might want to ask which one of these is larger, infinity squared or e raised to the infinity. And our answer will determine which one is the correct answer to my question. The answer to the limit will determine the answer to that question. All right, so because infinity over infinity is indeterminate, that means that L'Hopital can be applied. And limit as x approaches negative infinity of the original fraction equals the limit as x approaches negative infinity of the derivative of the top over the derivative of the bottom. So x squared differentiates to 2x, and e to the negative x differentiates to e to the negative x because the argument never changes. But don't forget the chain rule, times negative 1, because that's the derivative of negative x. All right, so this is, I can pull out that negative. Negative, the limit. Remember, you can pull out constants. In fact, we can pull out the 2 as well. We'll pull out the 2 from the numerator. You don't have to, but it makes the limit a little cleaner. So it's still x is still approaching negative infinity. We got rid of the 2, so it's just an x on the top. And we got rid of the negative 1, so it's just e to the negative x on the bottom. All right, well, that is still indeterminate because the denominator is still the same, and of course the limit as x approaches negative infinity of x equals negative infinity. So we have negative infinity divided by positive infinity, and that is just as indeterminate as positive infinity divided by positive infinity. So L'Hopital is going to get used one more time, and when we do that, that negative 2 stays out front. And we get 1 on the top, we get negative e to the negative x on the bottom. So we can pull out that negative, so negative 2 is positive 2. And we get 1 over e raised to the negative infinity, or positive infinity. Well, e raised to the infinity is infinity, so this is the same thing as 2 times 1 over infinity. And as we talked about a little bit while ago, any constant divided by infinity is going to equal 0. So that 2 became irrelevant, and the answer is 0. So as x goes towards negative infinity, this fraction approaches a value of 0. So to answer the question, which one of these infinities is bigger, exponential infinities beat polynomial infinities any day of the week. As long as the exponential base is greater than 1, then yeah, exponentials grow faster than polynomials. All right, great. So same fraction, but different infinity. This time we're going in the other direction. We're going in the positive direction. So let's, again, ask the question, what is the limit as x approaches infinity of x squared? As we already talked about, that's infinity. But what about as x approaches infinity of e to the negative x? That's going to be e raised to the negative infinity. And a lot of people are going to say, oh, that just means it's negative infinity, right? Wrong. When you take a negative exponent, it doesn't make a negative answer. It makes a fractional answer. This is the same thing as 1 over e to the infinity, which is the same thing as 1 over infinity, which is the same thing as 0. Ha! So this is actually not infinity over infinity or 0 over 0. This is infinity on the top and 0 on the bottom. This is not an indeterminate form. It is not indeterminate. Indeterminate. Instead, it is determinable. Right? We can figure this out because large numerators make our answer large, and small denominators also make our answer large. So this makes it infinity, and this makes it infinity, so this is actually infinity. This is not a L'Hopital problem, so the limit does not exist. Limit does not exist because the fraction heads to infinity as x goes to infinity. We've got two different forces, the numerator and the denominator, both of which are pulling this fraction towards infinity. In fact, if we rewrite our fraction as instead of x squared over e to the negative x, if we remember that that's the same thing as x squared times e to the positive x, that makes it a little bit more obvious that this is just infinity times infinity, which is of course infinity. So both of these functions are growing without bound, so when you multiply them together, their product will grow without bound. All right, good. So don't fall into the trap that you think that every limit now is going to be L'Hopital. This is not a L'Hopital problem. Alrighty, cool. Same kind of idea here with the same fraction with two different infinities. So what happens when we try the negative infinity? When we take the limit as x approaches negative infinity of the numerator, we get 6 times negative infinity plus 3 raised to the negative infinity. Remember that when you raise something to the negative infinity, it's like putting infinity in the denominator, so that's going to equal 0. So this is going to be 6 times negative infinity, which is a negatively infinite value. When we look at the denominator, same question, and in fact same answer, because we've got 3 times negative infinity plus 6 raised to the negative infinity, and that's also equal to negative infinity. So L'Hopital's rule applies. So if I zoom in on this, we move this up so we can get it out of the way a bit. So L'Hopital's rule applies, and we'll take the limit as x approaches negative infinity of the derivative of the top divided by the derivative of the bottom. Derivative of 6x is 6. Derivative of 3 to the x is 3 to the x times the natural log of the base, so times the natural log of 3. Similar thing happens down here. We get 3 plus 6 to the x times natural log of 6. All right, so what happens now when x goes to negative infinity? We've got, remember that this piece right here went to 0, and this piece right here went to 0. So that means we're going to take 0 times a constant, 0 times a constant. These guys right here go away. So the only thing that's left is 6 on the top and 3 on the bottom. So we get an answer of 2. Cool. So L'Hopital's rule gives us the answer of 2, and that is it for that limit. You can double check by graphing that function, that fractional function, and looking at the horizontal asymptote as x goes to negative infinity. So as we go to the left, you'll see y equals 2 is a horizontal asymptote. All right, trying this same fraction with positive infinity, we'll take the limit as x approaches infinity of the numerator is 6 times infinity plus 3 to the infinity. That's infinity plus infinity, which is definitely infinity. And we're going to see the same thing on the bottom, right? Whoa, too far. So we get limit as x approaches infinity of the denominator is also equal to infinity. All right. So if I were to move this down, we'll have a little bit. Oh, no, wrong button. Oops. Let's see. If we were to move this down to make a little bit more space for our work. Uh-oh. All right, I think I recovered from that little OneNote glitch. All right, so this is infinity over infinity, which means L'Hopital. And when we take the derivative of the top and the bottom, I think we already did that in the last problem, so we'll just go ahead and rewrite the same fraction again. 6 plus 3 raised to the x times natural log of 3. over 3 plus 6 raised to the x times natural log of 6. All right, so you're thinking, oh, well, this is just going to work out to be the same thing, but wait a second. This time, the 3 to the x and the 6 to the x don't go to 0, right? Because this time our x value is going to positive infinity. So this part's infinite, and this part is just a constant, okay? So this means that the plus 6 in the numerator and the plus 3 in the denominator are irrelevant. So it looks like we might have L'Hopital's rule again. So sure, let's go ahead and do it one more time. We could probably avoid L'Hopital's rule and just say, let's ignore this plus 6 and this plus 3, but L'Hopital's rule will take care of them. And we'll get 3 raised to the x times the natural log of 3 times another natural log of 3. And then we've got 6 raised to the x times the natural log of 6 times another natural log of 6. All right, and we still have infinity over infinity. We use L'Hopital's rule twice, and we're still looking at infinity over infinity. You're going to notice that multiple derivatives from here aren't going to help. It's just going to include more and more factors of natural log of 3 on the top and natural log of 6 on the bottom. So let's think about this. I'm going to factor out the fraction. This is a constant, so I don't really care so much about this. This is just going to hang out. It might be multiplied by our answer, or it might turn out that it doesn't matter at all. Let's take a look. Over here, we've got 3 to the x over 6 to the x. But since they're both being raised to the x, let's write it as 3 over 6 raised to the x. Now, we've got a constant of natural log of 3 over natural log of 6 squared times 3 over 6, which is 1/2, raised to the infinity. So 1/2 times 1/2 times 1/2 times 1/2 times 1/2. We're used to seeing infinity in the exponent, meaning that it goes to infinity. But actually, if the base is less than 1, between 0 and 1, then the more times we multiply, the smaller our answer gets, right? So instead of shooting off to infinity, this thing is approaching 0. So this is going to equal 0, so we've got this constant times 0. So the answer is 0. Okay? So basically, if we have an exponential expression where the exponent is going to infinity, if the base is greater than 1, like up here, e is greater than 1, then that means that e to the x is going to go to infinity as x goes to infinity. But if the base is less than 1, but greater than 0, then that base raised to the infinity is going to approach 0. So that should become obvious as you look at the graph of 1/2 raised to the x versus e raised to the x. So play around with that, and hopefully that makes some sense.